Everybody. Here we are doing 7.2 notes. 7.2 is on finding volumes by cross section. So the first thing let's talk about is what a cross section is. Cross section is like if you have a three-dimensional object and you slice it, right? If you take one slice of that object, then the cross section is what that slice looks like, right? So if you, some pretty obvious cross sections are if you had a cylinder and you sliced the cylinder horizontally, what would you get? You would get a circle, right? However, if you slice it vertically like such, you would get a rectangle, right? Similarly, if you had a cone and you sliced it horizontally, you would again get a circle. And if you sliced it vertically like such, what would you get? You would get a triangle, right? So we know some of them. Just like if you had a box, right, a rectangular prism, and you slice that, you would get a basically whatever, a square or a rectangle, depending on what the shape of this thing was here. So those are like real basic ones. You can think about a loaf of bread if it helps. A loaf of bread is like a solid object, a three-dimensional object, and when you slice it, you get to see their cross sections, right? So this first piece of bread here has a kind of a strange looking cross section. It's like a square with like some sort of circular thing on top. And this white bread over here has cross sections that are just pretty straightforward squares. All right, so that's the core of what we're learning today. Let me show you another little graphic thing here. The basic idea is we have a solid. It's kind of a weird shape, so we can't just find the area of the volume of it by using a known formula. So what we're going to do is we're going to cut it into sections, right? Cross sections. And if we can find the area of those cross sections, then we can add up all the areas of the cross sections and multiply by the width, right? Multiply by how wide each one is. That would give us a volume of each cross section, and add them all together. And eventually apply calculus to this idea of making each cross section skinnier and skinnier, and using an integral to add them all up. Right. So as you can see with this one right here, the base of this shape was a circle. The cross sections are squares, right? If I cut them, they'd be squares. I can change this and see what the shape looks like if the cross sections were triangles. Then you'd have this looking, you'd a shape that looks like this. We could also say, well, what does it look like if the cross sections are semicircles? Then it would look like, oh, that's just a half sphere, right? And then the last one is like rectangles, which looks pretty similar to the squares one, just a little bit lower down. All right, so that's what we're getting into. I want to show you one more demonstration thing here. Just a second. Let's see why it's not working. Okay, so what we're going to do in calculus is you're going to start with a region such as this, right? This region that is defined by this red function and this blue function. You're going to start with that, and they're going to tell you to build some sort of shape on top of it, right? It's kind of like building houses. We're going to build a shape on top of this region. The region gives us the base of the shape, and we're trying to figure out what the area is, right? So the first thing I'm going to build on top of this shape is a square. You can't see the square right now because we're looking straight down at it, but check out if we look at it from a different direction. You can see that it's a square. All right, so let me go back to this other, take a sideways look here, and we're going to go ahead and just start building squares on there, right? And we're going to build a whole bunch of squares. Let's move X over here. And as you can see, if we build enough of those squares on there, it kind of turns into a solid looking shape like this, right? Maybe let's reduce the squares a little bit so you can actually see them in there, right? And so that's what that shape would look like. And I could go, we could fill up this entire base with it, that's mostly what it would look like. And so you can see it's kind of like a weird looking loaf of bread. If you take one cross section of that bread, you basically have squares, right? Depending on how thick you slice it. We could also look at it if they are equilateral triangles, right? We're building equilateral triangles on it. Like this is what would be on your paper, right? You have to imagine that these equilateral triangles are coming out of your paper at you, right? Like this. And then basically what we're going to do is we're going to find the area of one of those equilateral triangles. And do you notice how like the base of the triangle is like the inside that region, right? It's just the distance between those two functions. The base is the distance between those two functions, right? So, and again, we could make a bunch of them. It'd end up making this solid looking figure. And we could also build semicircles on top. So there's the region. We build semicircles on there. And if we integrate, it's going to add up all those itty bitty little semicircles together, and it would tell us the exact volume of this region, right? So it's kind of cool. You can find volumes of things that aren't just rotated around. You can find volumes of a lot of different, more shapes than we used to be able to do. All right, so the trick to this is you need to be able to find the area of a cross section, right? So that's how we end up finding the volume. So let's go back to our notes here, and let's look at what we're going to actually be expected to do. Okay, so the way we're going to calculate the volume is we're going to integrate from A to B, right, where A and B will either be given or they'll be like the points of intersection. And all we need to find is the area of the cross section, right? If I can know that, if I can find the formula that tells me the area of that cross section, then I integrate it and I will get the volume, right? So like the general formula for this is just, A to B, the integral from A to B of A of X, which stands for the area. And this one is if we're using vertical cross sections, right? If we're cutting, let's say let's actually draw this neatly here. If I had my two functions like this and like this, then we're cutting it vertically in this case, right? Getting cross sections like that. And if we want, we can cut it horizontally, right? In which case, if we're cutting it horizontally like this, then we need all of our functions to be in terms of y, which is what this is saying, right? And then, same as before, these would be y coordinates instead of x coordinates, right? The A and the B are the y coordinates, not the x coordinates. All right, so the main idea here is we need to be able to find the area of these cross sections. So let's look at a couple of examples of like what it looks like to find the area of a cross section, right? So we're going to start with the coordinate plane, and we'll just do a very generic case here. Let's pretend I have f of x that looks like this, and let's pretend I have g of x, which maybe looks like that, right? Yeah, you might want some color on this. It definitely is helpful to have some color here. Okay, this is going to be the base of our solid, right? So this is like where we're going to build something on this base, right? We're not finding the area of this base. What we're trying to do is we're trying to find out what does each cross section look like. What's the area of a cross section? So we're going to cut one cross section like this. Let me use a different color. Let me use green. We're going to cut this cross section like this. And this is going to be the base of our shape, right? Let's go back to this little demo here, right? We're looking at, we have this shape, and the base of our shape, you can see if we're looking at straight ahead, the base of our shape is formed by our functions, and we're building something on top of it, right? We're building a house. Each house has a different kind of structure, right? This house has semicircles as a structure. So basically what we're going to do is we're going to build a house on top of that green piece. So I'm going to go ahead and draw that green piece. I'm going to lay it out right here. And I'm going to build a house on top of it, right? So this this is the base, and I'm going to build something on top of it, right? And they'll tell you what you're going to build on top of it. In this case, we're going to build a square where each side is bounded by the two equations. So I'm going to build a square on top of this base, right? So let's just go ahead and draw a square on top of my base. It's not a perfect square, but it's close enough. And so like we're kind of interested in, well, what's the other side length of this square, right? And knowing that it's a square, what should, this side over here be? Well, it should also be the same as whatever the base is, right? Because it's a square. The side lengths are the same. And then we'd ask, like, well, what's the area, right? And well, the area of a square is just simply the base squared, right? The base times the base. So in this case, we actually want to know, like, what is the base length in terms of our functions, right? So what is this green length right here? How do I determine this length? Well, it's basically just f of x, right? The base length is just going to be f of x minus g of x, right? Because f of x tells me the distance from the blue function all the way to the x-axis. G of x tells me the distance from the red function to the x-axis. And if I subtract g of x, then I'm just getting the distance between those two functions. So the base length in this case is just f minus g. The height of this function is, because it's a square, right? This is our height is over here, is the same as our base. So the height is also f of x minus g of x, right? Our height is the same as a base because it's a square. And our area of this cross section is base squared, right? So, or base times height if you want, but it's basically just going to be our base times our height. Let me try to write this neatly on here. It's just going to be f of x minus g of x, and then squared, right? Why is it squared? Because the area of a square is the base squared. The base is f of x minus g of x, right? The base is that. Okay, so that's the area of the cross section. We haven't done any calculus yet, really. We're just doing some algebra stuff. If I want to know the volume of the shape formed when we do this, I need to integrate, right, from a to b. We don't know what a and b are in this particular case because we don't have functions. Basically, I need to integrate the area function that I just came up with. So I'm integrating f of x minus g of x squared. Right, I'm integrating the area of that cross section that we just found. And if you do that, you will have the volume of this thing. All right. Let's do another example. And in this case, let's give ourselves a couple of functions so we can actually see what it looks like with letters and stuff. Okay, so maybe we'll just say let's let the first function be the square root of x, and let's let g of x be x squared. Right, so we're going to draw a quick little graph of what this looks like. Right, let's say this is 1, because these are going to intersect in a kind of a special way. F of x equals the square root of x looks like something like this, and g of x equals x squared looks something like that. You can find this out for yourself if you want, but they intersect at 1, 1. Okay, so we are going to make one slice here, right? And again, what we're doing is we're looking at this shape, right? And we're making a single slice on there, right? Just like this. And then what we're going to do is we're going to build a shape on top of it, right? In this case, we're going to build a rectangle, which this particular demonstration doesn't have a rectangle, but we're going to build, a shape right on top of that function using that green base that we have, right? So I'm going to draw that green base over here. Here's the green base. This is the base, which let's go to write what it's equal to. What is that base equal to, right? What is that green piece equal to? Well, it's equal to f of x minus g of x, right? The top minus the bottom. So in this particular case, the green base is equal to the square root of x minus x squared. That's what the base is. That's how we find the base. Again, the base is going to change depending on what the x value is. And the height of this function, according to our instructions here, the height is always twice the length, right? So if this is my length, then the height is always twice this length, right? So that means I'm going to build a rectangle up here where this height here is 2 times the base. So what would that look like? Well, it'd be 2 times whatever the base is, and the base is square root of x minus x squared. So that's the height. All right. So again, this is, we've already done all this, but the base length is x square root of x minus x squared. The height is 2 times the square root of x minus x squared. And the area of a rectangle is the base times the height, right? So the area of this rectangle is going to be the square root of x minus x squared times 2 square root of x minus x squared. And you could actually like simplify this a bit, right? If you the order in which we multiply doesn't matter, so I could just multiply the 2 first. And if I multiply the square root of x minus x squared times the square root of x minus x squared, if I multiply these two, that's multiplying something by itself, which means a simpler case of this would simply be 2 times the square root of x minus x squared, because we're multiplying that thing by itself, right? And so the volume would be the volume is going to equal the integral from 0 to 1. The reason we're going from 0 to 1 is the points of intersection are at 0 and 1 of the area of that base, which is right here. So of 2 times the square root of x minus x squared dx, right? And so we'd get out our calculator, our trusty calculator, and we'd put these functions on there. All right, so we're just gonna do, this one's not that bad, just to do it down here. Math 9, the integral from 0 to 1, and then we're doing, the integrand is 2 times the square root of x minus x squared, and this whole thing is squared, and then we're integrating with respect to x, and our volume is not very big. Our volume is simply whatever that number was, which I lost, 0.257, right? So our volume is going to be 0.257. Again, if you want units cubed, because it's a volume, right? Okay, so let's keep going, right? So we've done squares and rectangles, cross sections that are squares and rectangles. The next, we're going to do a semicircle. So our cross sections are going to be semicircles. So we're going to have 2 functions. Let's try different ones this time. Let's say f of x equals x, and let's do the other one, say g of x equals x squared, right? We're just coming up with some functions. F of x equals x looks like this, and g of x equals x squared looks something like that. Again, they intersect at 1, 1. What we're going to do is we're going to find one cross section, right? We're going to cut it once like this, and we're going to build a shape on top of that so we can find the area of that shape, right? Let me just go back to this thing again just so we can, visualize it. And we're taking this, something similar to this, right? We're cutting it. In this case, we're going to build a semicircle on top of it, right? So we're building that shape on top of that green thing, right? So we're building a semicircle on top of this, right? Now keep in mind that this base thing is top minus bottom, which means the diameter of this circle is x minus x squared, right? That's the diameter. Try to remember what's the formula for the area of a circle. Well, it's pi r squared, and since it's half a circle, you have to divide by 2. What you have to be really careful about here is x minus x squared is not the radius, right? This is the diameter. So the radius is half of the diameter. So in this case, the radius, and let's go ahead and cross these out because we don't want this. Like, there's no base and height in this case. There's a diameter. The diameter is x minus x squared. And then let's cross this one out and let's say, okay, well, this is going to be the radius. What is the radius going to be? Well, that's going to be x minus x squared over 2, right? Because the radius is half of the diameter. What's the area going to be? The area is going to be pi r squared over 2, right? So that's going to be pi. I put my radius there, and then I divide by 2. My radius is this thing, so that's what I'm putting in here, right? It's going to be x minus x squared over 2. And you could simplify this to, to make it look a little bit nicer, but maybe you're scared about making an error with your fractions or something like that, so you can just leave it like that if you want. The volume is just going to be the integral of this area that we found, right? So we're going to take this and we're going to integrate it over the interval, right? And again, our interval here is 0 to 1 because that's where these two functions intersect. I'll try to do an example where they don't go there so you don't think that's always the answer. And we're just putting the area that we found here. So this one has a pi in it and has x minus x squared over 2. This whole thing is squared because that's a radius squared, and then it's over 2 dx. If you were going to simplify this, you could easily bring out pi over 2 to the outside of the integral. Right, we're bringing out this pi and this 2 out here. And then you could square the top and the bottom separately, so that's x minus x squared squared, and then 2 squared is 4. So that 4 could also come out if you want, make it pi over 8. So let's go and do that, right? I'm going to erase this 4. I'm going to put pi over 8 here, right? You'll hopefully understand where that came from, right? This 2 right here is getting squared by this, becoming 4, and then it's being multiplied by that other 2 that's out there. So now all that's left is, don't forget the dx, and integrate this thing. Right, so let's figure out what the volume is. We're going to do the integral math 9 from 0 to 1 of, oh, I forgot the pi over 8 thing on the outside, so I'll just put it on the inside. It doesn't matter, it's the same thing. Pi divided by 8 times x minus x squared, the whole thing squared with respect to x. Yep, and we integrate and we get 0.013. So our volume is 0.013. Again, it's like units cubed. They're very rarely going to ask about this cubed units thing, right? Okay, let's keep going. Different shapes, different volumes. Okay, in this case, let's say f of x is 2 sine x. Let's make f of x 2 sine x. And let's make g of x a constant function, let's say 1, right? So if you're not sure what this looks like, then you should go to your graphing calculator and you can put both of these in there, right? You're going to say f of x equals y1 is 2 sine x, y2 is 1, and you should get a graph that looks like this. So our region is going to be sine looks like this, and g of x equals 1 looks like this. So this is the base of our solid, right? And what we need to find out at some points, so we don't have to do it right away, is these points of intersection, because that's what's going to be the limits of our integral. What we're going to do is we're going to slice it, right? We're going to take one little slice and we're going to build a shape on top of that slice. right? So what shape are we building this time? This time we're building a right triangle, isosceles right triangle. So remember, isosceles means two of the sides are the same, where the leg is bounded by the two regions. So this green piece is the leg, not the hypotenuse. So the green piece is one of the equal pieces, which means that our triangle has to go out like this, and this piece has to equal this piece, and then the hypotenuse goes over here. So remember, the base of this triangle, that green piece, is going to be defined by our functions sine x minus 1. Right, that's how we get that green piece. You take the height of sine x and you subtract 1, and that will give you the green piece. And since this is a right triangle, it's isosceles, meaning the height is the same as the base. We're also getting 2 sine x minus 1 for the height. The area of a triangle is 1/2 base times height. So the base length in this case is just what we already said, 2 sine x minus 1. The height here is also 2 sine x minus 1. Notice that if we multiply the base times the height, write it over here, it's going to be the base times the base, which an easier way of doing that is just squaring it, right? I'm going to put parentheses there. Squared, right? 2 sine x minus 1 times 2 sine x minus 1 is the same thing as 2 sine x minus 1 squared. So this is the area of our cross section, right? That's the area of this here. What we're going to do is we're going to integrate that, which is going to add up all the little cross sections together, which will give us a volume. So the volume is going to equal the integral of 1/2 times 2 sine x minus 1 squared dx. And again, we could put that 1/2 on the outside if we want. What we're missing is we're missing our limits of integration, right? We need to have these limits of integration, which are the points of intersection, right? Those green points of intersection. Let's go back to our calculator to figure out what they are. So we're just going to go to second trace. We're trying to find points of intersection, so we press enter. First curve, just be on the sine graph, press enter. Second curve, make sure you're on the line, press enter. Guess, we're going to get close to the first point of intersection we're interested in and press enter. And we're going to get 0.5235. So 0.523, let's round it up to 0.5236 so we don't miss too much information, right? So it's going to be 0.5236. And then we're going to do the other one, which means second trace intersect. Again, it just wants to know first curve, second curve, guess. Just make sure you get close to that second point of intersection. And we're going to get 2.61 rounded up to 8. 2.618. Right? So it goes up to 2.618. Right? So we put these on our calculator and we'll get the volume. Right? So let's go to Math 9. I need to be able to see this. We're going from 0.5236 to 2.1618, and we're doing 1/2, which is the same as 0.5 times 2 sine x minus 1. Be really careful with your parentheses, right? Just make sure they make sense for where they are. And we're getting a volume in this case of 0.506. So our volume is 0.5065. Right? You only need 3 decimal places, but there it is. Again, if you want, you can write units cubed. All right, let's keep going. Next one is isosceles right triangle, where the hypotenuse is bounded by the two equations. So it's a little bit trickier. Okay, for this case, we're going to make f of x be cosine x, minus 1. So cosine x minus 1. Keep in mind the minus 1 is outside the parentheses. And then g of x is going to be 0. try to remember from trig what cosine x minus 1 looks like. Like, you should be able to graph that without a calculator. But, you know, if you have to use a calculator, fine. Use a calculator. It's better than just sitting there being stumped and not knowing what's going on. Cosine x minus 1 is the graph of cosine, but then shifted down 1, right? So instead of starting at 1, it starts at -1, and then it goes up and down and up and down and so on and so forth, right? And then g of x equals 0 is basically the same thing as the x-axis. So if you trace those two, then we get something a little bit more than what I'm drawing here. You want to be careful because they didn't give us the, like, there's no bounds on here, right? So I'm gonna restart this real quick and show you what we have to be careful of. Let's look at the graph real quick. So here's cosine x coming up, and then 0 doesn't show up at all. I think, you know what, I was just graphing cosine wrong, because cosine usually starts at 1, right? So now instead of starting at 1, like cosine usually starts at 1, but now instead of starting at 1, it's going to start at 0, and then it'll go down from there. So it's going to start at 0 and go up and back down, and then g of x equals 0 is that line right there. So this is the region that we're interested in here. Again, we're gonna make a little slice, and we're gonna build a shape on top of that, right? We're gonna make a slice and we're gonna build a shape. So we're gonna turn that. So I'm gonna start drawing that shape over here. So first, let's consider what is the length of this little, you know, base here. What is that base? Well, it's again top minus bottom. In this case, it's the top is 0, right? That's g of x is on top this time, minus the bottom, which is cosine x minus 1. So this simplifies to negative cosine x plus 1, right? That's going to give us, that's how that simplifies, right? What are we doing? We're building a triangle on top where the hypotenuse is bounded by the two equations. So we're building a right triangle on top of this, but the hypotenuse is what's in our region, right? So that green piece is the hypotenuse of this triangle. It's isosceles, which means these two sides are equal, and we need to try to figure out what the area of this thing is, right? So let's do something real quick over here, right? If I have this triangle like this, and I'm trying to find the area, right? Let's say this whole thing is our base, right? This bottom piece is our base. To find the area of a triangle, you also need a height, or like an altitude that goes like this, right? If it's a right triangle, right? If we're doing that with this specific triangle, then what this altitude does is it actually divides our base perfectly in half, right? So like this will be base over 2, and this piece would also be base over 2, right? And then we need to figure out, okay, well, what is the height? Actually, I don't know if we need that base over 2 thing, but we'll see. What is the height of this, right? What is this height? Well, if you divided it perfectly in half, then you split this 90 degree angle over here in half, which means this is like a 45 degree angle. This one's 90, so this also has to be 45 degrees. So you have a 45, 45, 90 triangle, which means that the sides opposite the 45 degree angles are equal, right? So this side equals this side, so do need that base over 2. So we know that this is base over 2, which means that this altitude or height is also base over 2, right? Like, try to do this for yourself at some point, because it's you know, something you want to be able to recreate as soon as you can. So what does that mean about our altitude here? What's the height of this triangle? Well, it's base over 2, so it's going to be whatever our base was divided by 2, right? Our base, we said, was, after we simplified it, our base was this. So our height is going to be that same thing, but divided by 2. And the area of a triangle is 1/2 base times height. So in this case, 1/2 negative cosine x plus 1 times negative cosine x plus 1 over 2. So it's going to be, you write it kind of small, negative cosine x plus 1 and negative cosine x plus 1 over 2. Right, that's the base, this is the height. And we could clean this up a little bit and write, this is going to be, we can bring out this 1/2, so it's going to be 1/4 total, 1/2 times 1/2. And then cosine x plus 1, negative cosine x plus 1 times negative cosine x plus 1 can just be written as negative cosine x plus 1 squared because it's multiplied by itself. Alright, so then we go to, what's the volume? Well, the volume is going to be the integral of the area of that base, so it's going to be an integral of 1/4 times negative cosine x plus 1 squared dx. We need to know what are the points of intersection. So let's go back to our graph, right? It goes from 0, 0 to whatever this is here. And you can use your calculator to figure this out if you want. But we can kind of figure out what it is. Like, when does cosine get back up to this point? Like, when does it complete going down from 1 and then coming back up to where it started, right? And hopefully you're thinking like, oh, well, you know, it completes 1 period in 2 pi, so it should be 2 pi. But we can double check on the calculator, right? So we're going to do intersect. Actually, in this case, it's going to be a 0. I don't know if I plotted the other one on there. We already know that the first one's 0, 0. So let's do the one that's over here. And again, we're trying to get 2 pi. Like, we think it's going to be 2 pi, right? So one's left bound. This means you need to be left of the 0. Right bound means I need to be right of the 0. Guess means I need to be close. And if we do that, we get 6.28, which is 2 times pi, right? So it is, this is an angle of 2 pi, and we get 0 out of it in this case, right? So that means I'm integrating from 0 to 2 pi. We're going to do this on our calculator. So we're going to integrate math 9, 0 to 2 pi 1/4, which is 0.25. I like putting decimals in better. It just seems a little bit easier. Negative cosine x, close parenthesis, plus 1, parenthesis squared with respect to x. And we're going to get the volume is 2.356 units cubed. All right, we have one more example thing to do, and then we'll have a separate example. All right, for this one, let's say f of x is e to the x minus 4, and let's let the other function be natural log x, right? So hopefully you kind of know that e to the x minus 4 is the e to the x graph shifted right 4, and natural log of x looks kind of like the square root function, but it starts below the x-axis. It has like an asymptote at x equals 0 going to negative infinity, and then comes up, right? So ln x is going to look something like this, where it's 0 when x is 1, and then e to the x is going to look something like it's going to be shifted right 4, and it's going to be like something like this, right? And so this region here is going to be the base of our function. Let's go to start by finding the points of intersection this time, right? We could set them equal to each other and try to solve. But again, we have a graphing calculator, so let's do that. I'm just going to reset my window a little bit better so I can see the functions better. So there's e to the x. There's natural log of x. I think I do need to show a little bit of the negatives so I can get, so when I do the function thing, it actually shows me that. Where are they going to intersect? It doesn't even look like they're intersecting on the calculator, but they are. Let's hope the calculator doesn't freak out about it. So let's find some points of intersection. Let's do this one first because the calculator's not even showing that point of intersection. So first curve is that one, second curve is this one. Guess, it looks like it's intersecting down there. Good, it's not messing up on us. So this point of intersection down here is 1.0539 comma 0.0525. We don't really need the y coordinate. Then this point of intersection is going to be, again, second trace, intersect. Let's go way over here. Come on. Slow cursor. First curve, enter. Second curve, enter. Guess. That's pretty close. 4.3918. You want to try to get as many of these digits as you can. So otherwise, because you are approximating, and if you approximate too much, then your answer will be off. And if it's off by enough, then your answer will be wrong, right? If it's off by more than 3 decimal places. Okay, so that's our just setting up the problem. Again, what we're going to do is we're going to build a shape on top of this, right? So we're going to try to figure out what's the area of one cross section. So we're going to draw a little cut right there, and we're going to try to build a shape on top of that cut. I just want to go back to this thing one more time so you can see what we're doing, just in case you've forgotten. I think this is a really great visual, so you can see how these things work. Again, it's kind of not working. This one's actually going to look pretty similar to what we're doing. So here's our region that kind of looks like our region, right? And what we're going to do is we're going to slice it a little bit, right? And then we're going to build a shape on top, right? So you have that slice, and then if we turn it, what we're doing is we're building that shape on there, right? That's what we're doing. And then we're gonna just integrate it, which means we're gonna build a bunch of little triangles on there, which this thing is glitching out, but you can see that we're building a little triangle on that shape there. All right, so back to this. We're building a triangle on top of this, an equilateral triangle. So let's go and draw something that looks kind of like an equilateral triangle. Equilateral triangle has all the sides equal. What is the length of that gray piece? Well, it's the top minus the bottom. So in this case, it's going to be ln x is on top minus g of x, which is e to the x minus 4. Sorry, f of x, which is e to the x minus 4. That's that side right there, which means all the sides are the same as that. But we don't really care about those other sides. What we care about is we need to find the area of this, which again, the area of a triangle is still 1/2 base times height. So what we need to find is what's the height, right? We need that altitude, the perpendicular distance up. So let's go to the side again and do something similar to what we did before, right? If I have an equilateral triangle like such, right? Equilateral, and I draw this altitude. Again, it's going to divide the base in half, right? So if that whole thing was the base, then each one of these things is base over 2. But something you have to remember for an equilateral triangle is each angle was 60 degrees, right? And so this angle up here on the top, when I drew that altitude, it got divided in half, meaning that this is 30 degrees, right? And so what we have now is a 30, 60, 90 degree triangle. And so you need to remember, or just memorize something, but you need to remember, well, what's the relationship between the side and the height, right? So this side is base over 2. What's the height going to be? So try to go back to 30, 60, 90 triangles. If you know that this is base over 2, then it's kind of like on the unit circle, if this is the 1/2, then this one would be the root 3 over 2, right? So if this is base over 2, then this is going to be root 3 times the base over 2. And then this one would be the base, right? Because it was part of that equilateral triangle. So the altitude on this is the root 3 times the base over 2, right? So this will always be true for equilateral triangles. It might be something you want to write down or memorize. Same thing with the area for the height of the one that we did before, where that's just base over 2. So let's go over here The base length was our function subtracted. Our height is, remember what we had over there, root 3 times the base over 2, root 3 times the base over 2, which in this case is going to be square root of 3 times, I should do this in non-red, times ln x minus e to the x minus 4 power, right? That's our root 3 times the base. And then the area is the base times the height. So the area is going to be this guy times this guy, which again, please notice that you're multiplying ln x e to the x times ln e to the x twice, which is going to be, means you're squaring it. And so we're going to do 1/2 times root 3 over 2, and then those things get multiplied by each other, which mean, and they're the same thing, which means it's ln x squared. So it's going to be ln x minus e to the x minus 4 squared, because it's multiplied by itself. And the volume, right, once we have the area of the base, the volume is equal to the integral. Let me go ahead and put the constant on the outside this time. The constant is going to be root 3 over 4, right? When you multiply 1/2 times root 3 over 2, you get root 3 over 4 of ln x minus e to the x minus 4 squared dx, and our points of intersection, we're going to have to find out what those are. No, we don't. Just kidding. We already found that. I already found that in the beginning. So we found that over here, there, and there. So that's what we're going to put here and here, right? So it's going to be from 1.0539 to 4.39187. And that's we put on our calculator to get an answer. Let's just do it real quick. We're going to go back to our home screen here, Math 9, 1.0539, 4.39187. Oh, the root 3, okay, I'll put it on the inside. Square root of 3, divided by 4, make sure that 4 is not in the radical, times natural log x, close that parenthesis, minus e to the x minus 4 power, make sure the 4 is in the exponent, and then we're squaring that, and with respect to x. And what we're getting is the volume is equal to 0.4307 units cubed if you want. All right. What I'd like you to do is try this before you come to class. Okay, like these are on your paper. Please try them and see if you can get the answer. And if you have questions, come with questions. All right. Good luck.